Now that we've looked at the idea of heating and cooling buildings, let's take a look at a few examples. We're going to start with a very basic case. Let's suppose at the end of the day, time T0, when people leave the building, the outside temperature stays a constant at M0, the additional heating rate H is 0, and the furnace air conditioner rate U is 0. We want to determine capital T of T given the initial condition that capital T of little t0 is equal to capital T0. So the idea of this is the most basic case. We don't have any heating inside of the building, we don't have any air conditioners or furnaces running, and our outside temperature is constant. So we know that M is equal to M0, H is equal to 0, and U is equal to 0. Substituting these values into our formula for actually solving heating and cooling problems, we have it's equal to e to the negative kt times the integral of e to the kt times k m0 dt plus c. Integrating this gives me e to the negative kt times m0 times e to the kt plus c, which reduces to m0 plus c times e to the negative kt. We did have our initial condition, so we can stick that in. And while I won't show all the details of solving that, we do get our value for c, and we can reduce this to m0 plus t0 plus m0 times e to the negative k times t minus t0. For the next problem, we're going to find our building temperature, capital T of T. If our additional heating rate H of T is constant at H0, there's no heating or cooling, so U of T is equal to 0. And M varies as M of T is equal to M0 minus B cosine omega T, where B is a positive constant, M0 is the average outside temperature, and omega is equal to pi over 12 radians per hour. This would be a really good model for the situation during the spring or the fall where we don't have any cooling, and our temperature kind of goes up and down depending on if it's day or night. In this case, our Q of T is given by K times M0 minus B cosine omega T plus H0. If we let B0 be equal to M0 plus H0 over K, we can rewrite this as Q of T is equal to K times B0 minus B cosine omega T. In this case, K of B0 is going to be the average value for Q of T. Since it's the average, we have that K of B0 is equal to 1 over 24 times the integral from 0 to 24 of Q of T dt. From here, we can actually stick in this new form of Q of T into our solution for solving these heating and cooling problems. So we have that capital T is equal to e to the negative kt times the integral of e to the kt times kb0 minus kb cosine omega t dt plus c. And this is hard to integrate, but we can use computers and other things. We get that it's b0 minus b f of t plus c e to the negative kt, where f of t is cosine of omega t plus omega over k sine omega t all over 1 plus omega over k squared. If we assume that time t equal to 0 is midnight and the value of the temperature at midnight is T0, I can solve for c and get that c is equal to T0 minus B0 plus B of f of 0, which is the same thing as T of 0 minus B of 0 plus B over 1 plus omega over K squared. Now let's consider the last problem again, only this time we're going to assume that we installed a simple thermostat. And this simple thermostat is used to compare the actual temperature inside the building with our desired temperature, which we'll call T of D. If the actual temperature is below, then we kick on the furnace to supply heat to get to this ideal temperature. Otherwise, the furnace is off. If the ideal temperature is above our desired temperature, then the air conditioner will kick on and cool it. So that means the amount of heating or cooling supplied is proportional to the difference of temperature. So U of T is equal to KU times TD minus T of T, where this TD is our desired temperature, and KU is the positive proportionality constant. once again, we want to find our capital T of t. Sticking this into our basic form for heating and cooling, we get that the derivative of capital T is equal to K times m of t minus T of t plus h of t plus Ku times Td minus capital T of t. We can then rewrite this in standard form, where P is equal to K plus Ku, Q of t is equal to K times m0 minus B cosine omega t, plus h of 0 plus Ku Td. We are still changing the last problem, so we do still have this outside temperature modeled by this cosine function. And this is going to be much more difficult to solve, so we're going to start by introducing some constants. I'm going to let K1 be equal to K plus Ku. B2 is then Ku Td plus Km0 plus H0 all over K1. And B1 is equal to Bk over K1. And using these, I can rewrite Q as K1 times B2 minus B1 cosine omega t. And this now is going to look very similar to what I had in the last example, except for I'm going to be replacing K by K1, replace B0 by B2, and replace B by B1. So my solutions to my differential equation should be very, very similar, except that these constant terms are changed. So changing my constants gives me that capital T is equal to B2 minus B1 F1 of t plus C times e to the negative K1t. And in this case, F1 of t is equal to cosine omega t plus omega over K1 times sine omega t all over 1 plus omega over K1 squared.